In this lecture, we are going to study two examples where we apply the transport theorem. The first example is going to involve one rotation, and the second example is going to involve two rotations. So the first example is the following problem. Imagine that we have an arm which is hinged at a point O. O is the hinge point, and that hinge point is fixed to the ground. The arm rotates in the plane, and the angle that describes the rotation relative to the ground is the angle theta. Sliding on the arm is a collar. The collar is going to be located at a point P, and the distance between O and P is going to be R. So the goal of this problem is to determine the velocity and acceleration of the collar as viewed by an observer fixed to the ground. Now, the way in which these problems are set up and then solved is as follows, is that we have one rotation in this problem. So that implies that we need two reference frames. The reference frames that we're going to use are as follows. The first frame, which is what's going to be called the base reference frame, is going to be the ground. Now, the base reference frame is the frame in which we ultimately want the rates of change. The second reference frame is going to be the frame defining the first rotation, or I should say the frame that defines the first rotation. And that frame is the arm. So we're going to denote the ground by G and the arm by A. So for each frame that we are going to need in this problem, we have to fix a coordinate system to that particular frame. So that's important. So for each reference frame, a coordinate system needs to be defined that is fixed in one of the frames. In other words, we need a coordinate system we need one coordinate system fixed in each frame. So for the first coordinate system, we're going to we start with the ground, and remember the ground is our base frame. And the coordinate system that we're going to choose, if you look at the diagram here, we're going to choose the following coordinate system that's fixed to the ground. The origin of the coordinate system is going to be at point O. I'm going to choose EX to be along OP when theta equals 0. And that's basically in the diagram, the direction to the right. I'm going to pick EZ to be out of the page because that's the direction of the axis of the rotation, and then EY is going to equal EZ crossed with EX. Now I have the first coordinate system defined in the first reference frame, which is the base reference frame. The next frame is going to be the arm. And then I'm going to define the following coordinate system that's fixed to the arm. If you notice that the direction OP is along the arm, so that's a natural direction to pick for a basis vector. So we're going to put ER along OP. Notice that this is actually along OP, whereas when I did the ground, it was along OP when theta equals 0. So it's not the same. They're not the same direction. One is actually fixed to the arm, one's fixed to the ground. EZ is going to be the same as big EZ, and then E theta is going to equal EZ crossed with ER. If you draw a picture of this, here's what the picture looks like. There's EX, there's EY, EZ is out of the page. That's also the direction little ez. ER is the direction along the arm. E theta is the direction that is 90 degrees from ER in the plane. And the angle theta shows up in two places. One, it's the angle from EX to ER, and also the angle from EY to E theta. Okay. Now, in terms of the basis, ER, E theta, EZ, the position of point P relative to O is equal to RER. So the next thing we're going to do is we're going to compute the velocity of point P as viewed by an observer fixed to the ground. That's the first rate of change that we want. That's equal to the rate of change in the ground of the position of P relative to O. Now, because this position of P relative to O is expressed in a basis that's fixed in the arm, so it's fixed in frame A, the rate of change is going to be obtained by the transport theorem from the arm to the ground. So it's going to be d dt in A of Rp relative to O and A plus omega Ag crossed with Rp relative to O. Now d dt in A of Rp slash O is going to equal R dot ER. Now why does it equal R dot ER? It equals R dot ER because, remember, the basis ER E theta EZ is fixed to the arm. So the only thing that's changing, if I'm taking the rate of change of this vector as viewed by an observer fixed to the arm, is R. So I get R dot ER. Now if you look at the picture back here, you'll actually see that the angular velocity of the arm as viewed by an observer fixed to the ground is equal to theta dot EZ. Remember, theta dot's the angular rate, EZ is the axis of rotation. It's rotating about an axis that's normal to the plane of rotation. The plane of rotation is the EXEY or the ERE theta plane, and the direction normal to that is EZ. So that gives me that the angular velocity of A and G crossed with Rp relative to O, to G, is equal to theta dot EZ crossed with RER, which is equal to R theta dot E theta. So therefore, the velocity of point P as viewed by an observer fixed to the ground is equal to R dot ER plus R theta dot E theta. So next, we want to compute the acceleration of point P as viewed by an observer fixed to the ground. Well, that's equal to the rate of change in the ground of the velocity of p as viewed by an observer fixed to the ground. But again, if you look at the expression for the velocity of p, it's expressed in the basis er e theta ez, and that basis is fixed in frame A. So this is equal to d dt in A of the velocity of p in g plus omega ag crossed with the velocity of p in g. And that's just applying the transport theorem again from frame A to frame G. Now d dt in A of the velocity of p in G is equal to, let's look at the expression here. So the basis vectors are fixed if I'm in frame A. So I get r double dot er, and now this becomes a product. R dot theta dot plus r theta double dot times e sub theta. The angular velocity of A in G crossed with Vp in G is equal to theta dot Ez crossed with R dot Er plus R theta dot E theta, which is equal to, Ez crossed with Er is E theta, and Ez crossed with E theta is minus Er. So you get minus R theta dot squared Er plus R dot theta dot E theta, where I note that I flipped the order of the terms after I took the cross product. So Ez crossed with Er is E theta, I put that second, and Ez crossed with E theta is minus Er, I put that first. So then, the acceleration of point P, as viewed by an observer fixed to the ground, if I add these terms, is equal to R double dot minus R theta dot squared Er plus 2 R dot theta dot plus R theta double dot E sub theta. And just for clarity, let's make this look a little cleaner. So that's the acceleration as viewed by an observer. Point P is viewed by an observer fixed to the ground, and P is the collar. So that completes the first example. Now what we're going to do is we're going to move on, and we're going to do a second example. Now the second example is a little different, but it has certain elements from the first example. It's a little more complicated. So what I have is I have a disk, and let's see if I can draw this reasonably well. Okay. It's a circular disk. The center of the disk is at point O. There's a point on the disk which I'm going to call Q. Q is fixed to the disk. And then there's a particle or a point P which is sliding on the disk. And the distance from O to P is R, and the angle formed between OQ and OP is theta. The thing that to note here is Q is fixed to the disk, and theta is the angle from OQ to OP. Now, given that, and the disk also rotates relative to the ground with an angular velocity omega. So you can think of the ground as being out here somewhere. That's the ground. And then the disk is rotating relative to the ground, and then this angle theta, which describes the location of the particle, is actually measured from the direction of OQ. So you'll notice in this problem that there are two rotations. And because there are two rotations, that implies that we need three reference frames. And the three reference frames are as follows. The base reference frame, which is again the frame in which I want all the rates of change is the ground. The first rotation is defined by the disk, and the second rotation is defined by the plane that is plane formed by the normal to the disk and the direction OP. I'm going to explain this in more detail in a little bit, but for right now, I just want to describe it qualitatively, and then we'll get into more details. So G is equal to the ground, which, as you might recall, this is the base reference frame. And the coordinate system that I'm going to use, this time it's going to be a little different from the one I used before. The origin of the coordinate system is going to be at O. And now what I'm going to do is I'm going to define a direction EX, which is going to be fixed to the ground. It's going to be along OQ at time t equals 0. So what I mean by that is, pick a time, call that time t equals 0. Whatever direction OQ is pointing at that point in time, that direction is frozen to be in whatever direction that is at t equals 0. And I'm going to call that EX, and that's fixed to the ground. EZ is going to be out of the page. And then EY is equal to EZ crossed with EX. The next frame is going to be the disk, because that defines the first rotation. Here, the origin is going to be at O, and then I'm going to pick little ex to be along OQ, because Q is fixed to the disk. EZ is going to equal big EZ, and then EY is going to equal EZ crossed with EX. The third frame is going to be the plane, I'm going to call it A, and it's going to equal the OP EZ plane. Remember that a reference frame consists of at least 3 non-collinear points whose distance from one another is constant, and 3 non-collinear points define a plane. So in this case, what I'm going to do is I'm going to think of this plane as being the one that slices through the direction OP, and it's going to be normal to the disk. So it's slicing through. It's like, imagine you're just taking a slice on the disk diametrically, and you're going to go through OP. That's the plane I'm talking about. So the origin of this coordinate system is going to be at O. I'm going to define ER to be along OP. EZ is the same as in D. I mean, it's the same as used for the disk. And then E theta is going to equal EZ crossed with ER. So if you look at this picture here, imagine that here's little ex, here's little ey, there's the direction ER, there's the direction E theta. And the angle here is theta. The angle here is also theta. But remember that EX, EY itself is also rotating. So now, the position of point P relative to O is going to equal RER again, because it's a distance R in the direction of O to P. Now, you'll notice that this basis, ERE theta EZ, is fixed in frame A. So the velocity of point P as viewed by an observer fixed to the ground is equal to d dt in g of the position of P relative to O. But because the position of P relative to O is expressed in a basis that's fixed in reference frame A, which is this plane defined by OP and EZ, this is equal to RP relative to O, the rate of change of RP relative to O and A, plus the angular velocity of A and G crossed with RP relative to O. Now the first term, which is d dt in A of RP relative to O, is equal to R dot ER. The second term requires us to compute the angular velocity of frame A as viewed by an observer in frame G. But you'll notice something about this angular velocity. So the question is, what is that? Well, let's look at a couple of things here. So we have that the disk rotates relative to the ground We also have that the plane, the OP EZ plane, rotates relative to the disk. So as a result, the angular velocity of A and G is going to equal the angular velocity of D in G plus the angular velocity of A in D. Now the angular velocity of the disk as viewed by an observer fixed to the ground is what I defined as omega. If you go back over to this picture here, you'll see that I defined it to be omega. Now omega is out of the page, and this is going to equal omega EZ, where omega is equal to the magnitude of the vector omega, and EZ is the axis of rotation. The angular velocity of frame A as viewed by an observer fixed to the disk is equal to theta dot EZ. So this tells me that the angular velocity of A and G is equal to omega EZ plus theta dot EZ, which is equal to omega plus theta dot EZ. So therefore, the second term, the angular velocity of A and G crossed with the position of P relative to O, is equal to omega plus theta dot EZ crossed with RER, which is equal to R times omega plus theta dot E sub theta, which implies that the velocity of point P as viewed by an observer fixed to the ground is going to equal R dot ER plus R times omega plus theta dot E sub theta. Now next, the acceleration of point P as viewed by an observer fixed to the ground is equal to the rate of change as viewed by an observer fixed to the ground of the velocity of point P as viewed by an observer fixed to the ground, which is equal to, now once again you'll see that this vector Vp and G is expressed in the basis ERE theta EZ, and ERE theta EZ is fixed in frame A. So this is equal to d dt in A of the velocity of P in G plus the angular velocity of A in G crossed with the velocity of P in G. Now d dt in A of Vp G is equal to, well, if I'm an observer fixed to frame A, the only thing that are changing are these components. So I get R double dot ER plus R dot times omega plus theta dot plus R times omega dot plus theta double dot times E sub theta. And then the angular velocity of A and G crossed with V, P, and G is going to equal omega plus theta dot Ez crossed with the velocity in G of point P, which is r dot ER, plus r times omega plus theta dot E sub theta, which is equal to, once again, I'm going to do the cross products. Ez crossed with ER is E theta, Ez crossed with E theta is minus ER. So I get minus r times omega plus theta dot squared times ER plus r dot times omega plus theta dot E sub theta, where again I flipped the order. So I did Ez crossed with ER is equal to E theta. I put it in the second slot, and then I put the second term, I put it in the first slot after I did the cross product. So then the acceleration of point P in G is equal to, let's look at these terms here. I've got r double dot ER minus r times omega plus theta dot squared. So I got r double dot minus r times omega plus theta dot squared, the whole thing multiplied by ER. And then the second term, I've got r dot times omega plus theta dot. I've got another r dot times omega plus theta dot. So I've got 2 r dot times omega plus theta dot. R dot times omega plus theta dot. That takes care of those two terms. Plus r times omega dot plus theta double dot, and then the whole thing times E sub theta. So you can see here that the now the velocity takes into account both rotations. The velocity and the acceleration takes into account both rotations. So the sort of picture that I wanted to see here is that we had two examples. The first example had one rotation, and then 2 reference frames. The second example had 2 rotations, so had 3 reference frames. And in order to be able to do the second problem, we had to use, so we needed to use angular velocity addition in order to compute the angular velocity of the last frame, which is rotating relative to the second frame, which in turn was rotating relative to the first frame. So it's important that we actually needed to use angular velocity addition in order to do that example. And it's important to keep in mind that as the rotations build up, sometimes the rotations aren't necessarily going to be about the same axis, and so these rotations are going to be more complicated. But nevertheless, when you have more than one rotation, you need to add the angular velocities that define each of the successive rotations. So for the purposes of this discussion, we kept the rotations all in the same plane just to make it a little easier for starters to be able to see what's going on. And in the future, we're going to be looking at problems where the axes of rotation are not necessarily going to be all aligned, and we're going to have to be a little bit more careful about how we define the rotations, and we're going to have to be more careful about how we actually add angular velocities to figure out what's actually going on, and that's going to come a little bit later. But for right now, this lecture is about problems at this level of complexity, and we'll see problems of greater complexity as we move forward.